So here's what we're doing. Today, we'll explore and explain 7 popular sorting algorithms, talking about their mechanics as well as their pros and cons. How sorting algorithms are evaluated. Sorting algorithms are typically evaluated based on time complexity and space complexity. Time complexity indicates how the algorithm performs in the best and worst case scenarios in terms of the number of operations required to sort the list. Base complexity refers to the amount of additional memory the algorithm consumes. For instance, in bubble sort, the worst case time complexity is big O of n squared, where n is the number of items in the list. The best case time complexity for bubble sort is big O of n, which occurs when the list is already sorted and only one pass-through is required. In the worst case, if the list is completely unsorted, bubble sort will need multiple passes to sort all the elements. Bubble sort is one of the most well-known but inefficient sorting algorithms, often used to teach sorting concepts. The algorithm works by iterating through the list, comparing adjacent elements, and swapping them if they're in the wrong order. This process repeats until the entire list is sorted. The worst case time complexity of bubble sort is big O of n squared. Going back to the graphs, that we can see that this would make it highly inefficient with large lists. However, its simplicity makes it a useful educational tool. For practical purposes, I'm gonna be honest, you're just better off going with a faster sorting algorithm. Selection sort is another easy to understand sorting algorithm that works by repetitively selecting the smallest or largest element from the unsorted portion of the list and swapping it with the first unsorted element. It divides the list into a sorted and unsorted section, continually shrinking the unsorted section. Despite its simplicity, selection sort also has a time complexity of big O of n squared, in both the best and worst cases, making it inefficient for large datasets. Insertion sort is similar to selection sort in that it builds the list incrementally. It iterates over each item in the unsorted portion of the list, finding the correct position for each element in the sorted section by comparing it with the elements already placed. The worst case time complexity of insertion sort is big O of n squared, but it can perform well for small or nearly sorted lists with a best case time complexity of big O of n. Cocktail sort is another variation of bubble sort that sorts in both directions on each pass through the list. After completing a pass from left to right, it then makes a pass from right to left, progressively sorting the list from both ends. This algorithm has a worst case and best case time complexity of big O of n squared, making it inefficient for large datasets, but it can be faster than bubble sort in practice, especially when the list is partially sorted. Comb sort is an improvement on bubble sort, which aims to eliminate the small values that are in quotations stuck at the end of a list. It uses a gap sequence to compare elements that are further apart, which helps reduce the number of comparisons and swaps. The worst case time complexity is big O of n squared, but the average time complexity can be better than bubble sort, making it a more efficient option in certain cases. Now, this is a little more complicated than the last. Merge sort is a highly efficient divide and conquer sorting algorithm. It divides a list into smaller sublists and recursively sorts each sublist. It then merges them back together in sorted order. The worst case and best case time complexity of merge sort is big O of n log n, meaning that as the size of the dataset grows, the time taken increases in proportion to that size of the list multiplied by the logarithm of that size. A logarithm is a way of counting how many times you can divide the input in half, or any other base, before you get down to a single item. This explains why merge sort performs well, because it divides the list into smaller pieces, and each division only requires a logarithmic number of steps. The divide and conquer approach allows it to perform well regardless of the initial state of the list, as it always performs the same number of operations. Quicksort is another divide and conquer algorithm that uses pivot elements to partition that list into two sublists. One with elements less than the pivot and one with elements greater than the pivot. These sublists are then sorted recursively. The worst case time complexity of quicksort is big O of n squared, when the pivot is poorly chosen, but in practice, with good pivot selection, often performs at big O of n log n on average. This makes quicksort a highly efficient algorithm, especially for large datasets. Sorting algorithms are crucial tools in programming, each with its own strengths and weaknesses. The best choice depends on factors such as the size of the dataset, the expected order of the elements, and resource constraints. While algorithms like merge sort and quicksort are typically used in practical applications due to their efficiency, simpler algorithms like bubble sort and insertion sort can still provide valuable lessons in understanding sorting principles. Anyways, I hope you guys enjoyed, and hopefully I'll see you in the next one. See ya!